Well, in this video, we're going to talk a little bit about fluid pressure and fluid force. When an object is submerged in liquid, such as the ocean, the weight of the water exerts a hydrostatic pressure on the object. If a very small plate is at a depth d, say a constant depth, in a liquid of density rho, mass per volume, then the force on that plate is given by F is mass times the acceleration of gravity, which is the depth times rho times g times a. Okay, where g is the acceleration due to gravity, a is the area of the plate. It turns out that this force applies equally in all directions. The pressure is defined to be this force divided by the area, so the pressure is just d times rho times g. If we let delta represent the weight density, weight per volume, which is basically d times rho, rho times g, then we have the pressure is delta times g. Okay, whoops, where are we going? Back here. In the SI system, international system, the unit of force is the Pascal. 1 Pascal is 1 Newton per meter square. 1 Pascal is quite small, so a kilopascal, kp, is often used. The density of pure water in the metric system is 1 gram per cubic centimeter, which translates to 1,000 kilograms per cubic meter. Thus, the pressure at 1 meter in water, okay, that's the pressure at 1 meter in pure water, is 1 meter times 1,000 kilograms per cubic meter times 9.8 meters per second square is 9,800 pascals, or 9.8 kilopascals. So it goes, increases by 9.8 kilopascals every meter you go down. In the American system, the weight density of water is 62.4 pounds per cubic foot. So if a plate is horizontal, so that it's a constant depth, then we could just calculate its area, multiply by the pressure, which is a constant, to find the force on the top of the plate. However, if the plate that is not at a constant depth, say that it's a vertical plate, for example, then the pressure is going to be variable. There's going to be more pressure on the bottom of the plate because it's submerged further in the liquid than the top. And this is going to lead to an integral calculus solution for computing the force on the plate. So I'll do a couple of examples. So let's start with this one. We have an oil tanker, or oil tank, that's in the shape of a right circular cylinder of diameter 4 feet. We want to find the total fluid force against one end of the tank when the axis is horizontal, and the tank is half filled with oil of weight density 50 pounds per cubic foot. So here's the end of the tank is graphed here, and the oil is filled up to the shaded part here. So we're going to see how much pressure is put on. There's basically nothing at the surface here, but higher and higher pressure as we go down here. And we want to actually, what we want to find is the total force on here. So I get to choose my coordinate system. I'm going to choose my origin at the center of the circle. So the circle is just then, x squared plus y squared equals 2 squared. And we can look at this picture. So we take a strip at a constant depth. That would be this strip across here. Let's say that total width is W. And it's at a depth D. Well, D is just minus whatever Y is, the opposite of Y. So D is the opposite of Y to make the depth a positive number, because Y is negative down here. And the area of the strip is some thickness delta Y, or we'll let it be dy, let's say, and then times the width. Well, the width is twice the x value of this point B, wherever B is along the side here. And if you're on this side of the arc of the circle, x is the square root of 4 minus y squared. That'll give you the positive value over here. And that'll give you half of w, so double that to get the width. Multiply by dy to get an area, and then do the depth times the density times that area. So the depth is minus y feet. The density is 50 pounds per square foot. That's the weight density. The area then is that width times the height of dy. Now if you look, the units, I put the units in to show you that they work out. dy has units feet, the width has units feet, the depth has units feet, so that's cubic feet. We multiply by pounds per cubic feet, the cubic feet cancel, and we get pounds. So just dropping all the units, let's see what we end up with. Well, this square root of 4 minus y squared right here can be rewritten as 4 minus y squared to the 1/2. The 50 I'm going to bring out front. I'm going to leave the 2 in with the dy. I'm going to leave the minus and the y in there as well. So this altogether is going to be du when I let u be 4 minus y squared. See, if u is 4 minus y squared, du is, well, 0 plus negative 2y dy, right? So then this becomes u to the 1/2. This becomes du. I need to change my limits to be u limits now. If x is 0, I plug in 0 here for y, and we see that u is 4. And if I plug in x is negative 2, we see that u is 0. So this is going from 0 to 4 now. Well, an antiderivative is u to the 3/2 multiplied by 2/3. 2/3 times 50 is 100/3. And evaluate from 0 to 4. Just plug in the 4 and the 0, evaluate and subtract. So that's 0. 4 to the 1/2 is 2, to the 3rd is 8, times 100/3 is 800 pounds, or 266.6 repeating pounds. And that's the total amount of force on the end. Let's try another one. You might try this one yourself. Suppose that a dam is shaped like an isosceles trapezoid. The height is 100 feet. It's 350 feet long across the top and 200 feet long at the bottom. When the water level behind the dam is all the way up to the top, what's the total force that the water exerts on the dam? And notice it really doesn't matter how big the lake is in terms of how far out it goes. It's if this lake is, you know, a meter wide or 100 miles wide, it doesn't matter. It has something to do just with the depth. Okay, so go ahead and see if you can figure that out. Come back when you have an answer and check it with the work here. Press pause now. So here's what the shape looks like. There's your trapezoid. It's 200 across the bottom, 100 up and down this way, and altitude. And across the top, it's 100. Let's see, 350. So if I break this down here and make right triangles, that leaves 200 in the middle. 150 is split equally as 75 here and 75 here. Now we take a strip here going from H to G across here. That's the width there that we want to find. Ultimately, it's all the way across here, which, if you notice, it's actually 200 plus 2 of the x's. Okay, if x is this distance across here from I to G. The depth is H here, so that leaves this remaining piece down here is 100 minus H. It's 100 all the way up from here to here. Notice that we have some similar right triangles here. X is to 100 minus H as 75 is to 100. So that gives me this proportion right here, which I can solve for X in terms of H. X is, well, that's 0.75 times 100 minus H. Distributing that 75 minus 0.75 H for X. So now what's the width all the way across? Well, we've got the 200 across the middle part of the rectangle part plus 2 of these x's, and one on both sides. So the width is 200 plus 2 times that x, and distributing, that's 150 plus 200 is the 350, and it's minus 1.5 times the h. Okay. Now, so see if that makes sense. If we start at 0 for h, we're at the top, it's 350. If we go all the way down to the bottom at a depth of 100, 350 minus 150 is 200 across the bottom. So that does make sense. We know that the weight density of water is 62.4 pounds per cubic feet. And we take our representative horizontal strip to compute its area, which is just the W times dH in this case. We multiply this by the depth H to get a volume, which is then multiplied by the density to get force. And this is our integral right here. So it's 62.4, that's pounds per cubic foot. We have H feet deep, we have this many feet wide, and DH feet thick. Okay, so pull the 62.4 out front, distribute the H. We just got a polynomial, not too hard to wrap that up. Add 1 to the power, divide by the new power, that's 175 H squared. Same thing here, this goes up to cube, divide by 3, that's 0.5. and then evaluate from 100 to 0, plug in 100, plug in 0, the zeros go away, and you can see the details worked out there. And when dust settles, it's 78 million pounds. It's the total force on the entire, applied by the water on the entire dam. Okay, so hopefully that gives you a quick introduction of how to set up some calculating force on a surface that's submerged in some kind of a liquid.